What is a chemical bond? What are the different types of bonds that can form? And why do bonds between atoms form? The simplest definition for a chemical bond is forces that hold atoms together. There are two distinct ways that atoms can interact to form bonds, either by sharing the outermost electrons, called valence electrons, to form covalent bonds, or by transferring valence electrons from one atom to another to form ionic bonds. An example of an ionic bond is lithium fluoride. Here we see lithium transfer an electron to an atom of fluorine to yield a positively charged lithium ion and a negatively charged fluoride ion. The charged particles are then strongly attracted to each other to yield neutral aggregates. The driving force for the formation of this ionic bond is stability. The resulting ionic compound is more stable than the neutral atoms for lithium and fluorine. In the next example of ionic bonding, 2 electrons are transferred from magnesium, 1 to each atom of chlorine. Here, 2 negatively charged atoms of chlorine come together with a +2 charged ion of magnesium to form the very stable, electrically neutral molecule of magnesium chloride. While it is true that chlorine and fluorine have a strong desire for the extra electrons donated by lithium and magnesium, and that the very strong attraction of the oppositely charged ions are both driving forces for the formation of the ionic bond, a simpler explanation does exist for why ionic compounds form. To answer why ionic compounds form and why they are so stable, we need to examine the periodic table. Simply stated, atoms want to adopt the electron configuration of a noble element, and they will do this by gaining or losing electrons. Examining the abbreviated electron configurations for the previous lithium fluoride example clearly demonstrates this principle. When lithium fluoride formed, lithium lost an electron to adopt the electron configuration of helium, and fluorine gained an electron to adopt the electron configuration of neon. Thus, both lithium and fluorine have adopted the very stable electron configuration of the nearest noble element. But how do we know if an ionic bond or a covalent bond will form given a molecular formula? To answer this question, we need to look at electronegativity values for the elements. Electronegativity is defined as an atom's ability to attract electrons within a chemical bond. From the periodic table, we see that values for electronegativity tend to decrease going from right to left and down a family or group. The values range from 4.0 for fluorine to 0.7 for cesium. To predict what type of bond will form, we need to examine the difference of electronegativity values between the atoms. If a difference of approximately 2.1 or greater is calculated between the two atoms, then an ionic bond will form, which is typical for a metal and a nonmetal. In the previous example, the electronegativity difference between lithium and fluorine is 3.0. Thus, we can predict that an ionic bond will form. If 2 atoms are combined with electronegativity differences greater than 2.1, we can even predict their final empirical formula, the simplest ratio these elements will combine. For example, what will the formula be if lithium and oxygen combine? First, the difference of electronegativity values is greater than 2.1, 2.5. Thus, an ionic bond will form. When examining the electron configuration for each atom, we see that lithium will want to lose 1 electron to adopt the electron configuration of the noble element helium, and oxygen will want to gain 2 electrons, which oxygen will get by combining with a second atom of lithium to adopt the electron configuration of the noble element neon. Thus, they will combine in a 2-to-1 ratio to form an electrically neutral compound. If the difference of electronegativity values between two atoms is less than 2.1, then a covalent bond can be predicted. For example, given the formula H2, which has an electronegativity difference of 0, we predict that a covalent bond will form. But why will this bond form at all? Here, two atoms of hydrogen come together to share two electrons, forming a covalent bond. When the hydrogen bond is formed, both atoms of hydrogen adopted the electron configuration of the nearest noble element helium, because both atoms of hydrogen now have access to an additional electron. However, it is more convenient to represent the covalent bond by a line. The line represents two electrons being shared by each atom. Therefore, there are two electrons around each hydrogen atom. We say that the atoms have full valency. Lewis diagrams like these are developed more fully in subsequent chapters. To further deepen our understanding of the covalent bond, let's plot the internuclear distance between the two hydrogen atoms versus energy. As the two individual atoms become closer to each other, the two electrons can be shared, which is a stabilizing effect that lowers the relative energy. In addition, we find that there is an ideal distance for the sharing of the electrons between the two hydrogen atoms at around 0.074 nanometers. This energy minimum is called the bond length. However, notice that the energy profile spikes very quickly when the two atoms are too close due to repulsion of the adjacent positively charged nuclei, which is a destabilizing effect. Are electrons always shared equally when a covalent bond forms? To answer this question, let's examine hydrogen fluoride. The difference of electronegativity values, 1.9, indicates a covalent bond. However, fluorine has a higher electronegativity value than hydrogen, meaning it has the ability to attract electrons to itself, much more than the hydrogen atom. Thus, the electrons are not shared equally, and the electrons spend more time on the fluorine atom. The buildup of electron density on the fluorine atom causes a partial negative charge, and a loss of electron density around the hydrogen atom results in a partial positive charge, commonly called de-shielding. Thus, a polar covalent bond is formed. Here the arrow indicates a dipole pointing toward the more electronegative element. Now we can break down the covalent bond into two categories on our chart: polar and nonpolar covalent, based on the difference of electronegativities of the atoms. These types of bonds can also be represented visually: an ionic bond with no sharing of electrons, a polar covalent bond with unequal sharing of electrons, and nonpolar or pure covalent with equal sharing of the electrons. Our goal in this chapter was to demonstrate why and how a bond will form. In addition, we have been able to predict what type of bond will form by examining the difference of electronegativity values of the atoms involved. An understanding of these three basic types of bonds, nonpolar, polar, and ionic bond, is essential when studying chemistry. Lewis diagrams are a convenient way to indicate the gross connectivity of atoms within a molecule that utilizes covalent bonds. After all, different structural and geometric isomers can be imagined from relatively simple molecular formulas, which are explored in later chapters. To be able to draw these diagrams, one first needs to learn how to write Lewis dot diagrams for the elements. A Lewis dot diagram for an element indicates only the valence electrons. Examining the element's abbreviated electron configuration allows us to ascertain the number of valence electrons present. Notice that by simply counting from left to right across the periodic table until the element in question is reached, yields the same result. For example, carbon is 4 spaces over, thus it has 4 valence electrons. For most elements of the periodic table, we imagine a box around the element. Each side of the box can hold 2 electrons, which are represented by dots. Notice that as you go down the chart, the first 4 electrons are distributed on each side of the imaginary box. Then electrons begin to become paired, starting with the 5th electron. Some of the more common elements used in making covalent bonds from the first 2 rows of the periodic table will help develop covalent bonding principles. For example, each atom of fluorine in F2 has 7 electrons, which are placed around each atom. Each atom now needs 1 more electron to adopt the electron configuration of neon. Each atom of fluorine will gain access to that electron by sharing a pair of electrons. In fact, all of the halogens will form a single covalent bond for the same reasons stated. A general set of rules has been developed to guide us when drawing Lewis structures. Given a molecular formula, count the total number of valence electrons, use 2 electrons to form a covalent bond between atoms, and then give full valency to the atoms using the remaining electrons. Let's explain and apply these simple rules for the molecular formula for water. Water has a total of 8 valence electrons. Again, a shortcut for this calculation is to count from left to right on the periodic table for each atom. For oxygen, it is 6 spaces, and for hydrogen, it is 1 space. Therefore, 6 plus 1 plus 1 equals 8. Because each hydrogen can form 1 bond, let's bond each hydrogen atom to the oxygen atom. At this point, we have used a total of 4 electrons and have 4 remaining. After placing the remaining 4 electrons around oxygen, it has gained full valency. Or we could say oxygen has adopted the electron configuration of neon because it now has 8 electrons around it, sometimes called the octet rule. In addition, each hydrogen atom has 2 electrons, giving them full valency, or we could say that they have adopted the electron configuration of helium, sometimes called the Duet rule. Ammonia has a total of 8 valence electrons. Again, a shortcut for this calculation is to count from left to right on the periodic table for each atom. For nitrogen, it is 5 spaces, and for hydrogen, it is 1 space. Because each hydrogen can only form 1 bond, let's bond each hydrogen atom to the nitrogen atom. At this point, we have used a total of 6 electrons and have 2 remaining. After putting the remaining 2 electrons around nitrogen, it has gained full valency, or an octet. In addition, each hydrogen atom has 2 electrons, giving it full valency. For N2, there are a total of 10 valence electrons, 5 for each nitrogen atom. Bonding the 2 nitrogen atoms requires 2 electrons, and we have 8 remaining. Let's try putting 4 electrons around each nitrogen atom. Does each nitrogen atom have 8 electrons for full valency? No, each nitrogen has only 6 electrons. Thus, let's try to place 2 more electrons between the 2 nitrogen atoms, creating a double bond. Now we have used 4 electrons with 6 remaining. Placing 3 electrons on each nitrogen atom means that each nitrogen atom now has 7 valence electrons, which is closer to our goal of 8. Now let's try a triple bond. We have now used 6 electrons with 4 remaining. Placing 2 of the remaining electrons on each nitrogen atom gives full valency for each nitrogen atom. Or we could say it has adopted the electron configuration of neon, because each atom now has 8 electrons around it. As you can see, sometimes a trial and error approach is necessary for the last step. For carbon dioxide, there are a total of 16 valence electrons, 4 for carbon and 6 for each oxygen atom. Let's place the unique atom carbon in the middle and then bond an oxygen atom to each side. At this point, we have used a total of 4 electrons and have 12 remaining. Let's try putting 6 electrons around each oxygen atom. Now we check to see if each atom has full valency. While each oxygen atom does have 8 electrons, carbon only has 4 electrons. In fact, there is no way to arrange the remaining 12 electrons so that each atom is able to obtain full valency. Thus, let's try to place 2 more electrons between the oxygen and carbon atoms, creating 2 double bonds. Now we have used 8 electrons with 8 remaining. Placing 4 electrons on each oxygen atom means that each oxygen atom now has 8 valence electrons, and the carbon atom has 8 electrons. Thus, full valency for each atom has been achieved. Again, a trial and error approach was necessary for the last step. For N2F2, there are a total of 24 valence electrons. Although it appears that there may be several ways to assemble these atoms, one first needs to realize that each fluorine atom can only form 1 bond, and nitrogen can form 3 to obtain full valency, which reduces the possible ways these 4 atoms can be bonded together. Therefore, let's bond both nitrogen atoms in the middle and bond the fluorine atoms on each side. At this point, we've used a total of 6 electrons and have 18 remaining. Let's put 6 electrons around each fluorine atom so that each fluorine atom has full valency, which now leaves 6 electrons. We could try placing 3 electrons on each nitrogen atom. However, full valency will not be met for the nitrogen atoms. Thus, let's try to place 2 more electrons between the 2 nitrogen atoms, creating a double bond, which means we have used 20 electrons with 4 remaining. Placing 2 of the remaining electrons on each nitrogen atom gives full valency for all atoms and uses all 24 electrons. When calculating the number of electrons for cyanide, one needs to add the 4 electrons from carbon, the 5 electrons from nitrogen, and then add the extra electron that is responsible for the -1 charge, for a total of 10 electrons. After we bond carbon and nitrogen, we have a total of 8 electrons left. Let's try putting 4 electrons around each atom. However, each atom only has 6 electrons. Thus, let's try to place 2 more electrons between the 2 atoms, creating a double bond. Now we have used 4 electrons with 6 remaining. Placing 3 electrons on each atom means that each atom now has 7 valence electrons, which is closer to our goal of 8. Thus, let's try a triple bond. We now have used 6 electrons with 4 remaining. Placing 2 of the remaining electrons on each atom gives full valency for each atom, or we could say they have adopted the electron configuration of neon. We now need to indicate that cyanide has a -1 charge. To do this, we place our Lewis structure inside a set of brackets and the charge outside of the brackets. As we have demonstrated, drawing Lewis structures can sometimes require a trial and error approach. Just remember a few simple steps. Count valence electrons, bond the atoms, and place the remaining electrons around each atom to achieve full valency, which may require multiple bonds between atoms. Remember, a trial and error approach is often necessary. When drawing Lewis structures, it is convenient to always keep in mind some generalizations and exceptions for common elements. The first row element hydrogen will always make 1 bond. The octet rule for second row elements such as carbon, nitrogen, oxygen, and fluorine will always hold, and those elements cannot exceed 8 electrons. For some second and third row elements, such as beryllium, boron, magnesium, and aluminum, they can have fewer electrons than the octet rule. Third row elements, such as sulfur and phosphorus, can follow the octet rule. However, they can exceed 8 electrons. It is worth our efforts to work several examples in this chapter that are exceptions to the octet rule. First, we should examine the difference in electronegativity values of this metal and nonmetal to determine if an ionic or covalent bond will form for BeCl2. With a difference of 1.5, we can predict a polar covalent bond. Beryllium has 2 valence electrons, and each halogen has 7. 4 electrons are used to make the 2 bonds. Thus, the remaining 12 electrons are distributed over the 2 chlorine atoms. However, the central atom now only has access to 4 electrons and does not adhere to the octet rule. Therefore, beryllium is an exception to the octet rule. For BeCl3, we should first examine the difference in electronegativity values to determine if an ionic or covalent bond will form. With a difference of 1.0, we can predict a polar covalent bond. Boron has 3 valence electrons, and each halogen has 7. Six electrons are used to make the 3 bonds. Thus, the remaining 18 electrons are distributed over the 3 chlorine atoms. However, the central atom only has 6 electrons and does not obey the octet rule. As we would expect, aluminum, which is in the same family as boron, behaves similarly because it also has only 3 valence electrons. Therefore, boron and aluminum are exceptions to the octet rule. Using the same kind of approach we have done for previous examples, PF3 has 26 electrons. 6 electrons are used to form the 3 bonds, 18 are used to give full valency for the fluorine atoms, and the 2 remaining electrons are placed on the phosphorus atom to yield full valency. Using this same approach for PF5, we calculate 40 valence electrons. Because fluorine can form only 1 bond, 10 electrons will be used to form 5 bonds to phosphorus. Placing the remaining 30 valence electrons around the fluorine atom allows each fluorine to have full valency. Thus, phosphorus can have 8 electrons, or it can break the octet rule by having 10 electrons. Again, we use the same kind of approach we have done for previous examples. SCl2 has 20 electrons. 4 electrons are used to form the 2 bonds, 12 electrons are used to give full valency for the chlorine atoms, and the 4 remaining electrons are placed on the sulfur for full valency. Using this same approach for SCl6, we calculate 48 valence electrons. Because chlorine can form only 1 bond, 12 electrons will be used to form 6 bonds to sulfur. Placing the remaining 36 valence electrons around the chlorine atoms allows each chlorine atom to have full valency. Thus, sulfur can have 8 electrons, or it can break the octet rule by having 12 electrons. The noble elements are often thought of as inert or unreactive. However, as you go down the family of nobles, they become increasingly more reactive. For example, let's draw the Lewis structure for XeF4. There are a total of 36 valence electrons, and 8 of them must be used to create the 4 bonds. 24 electrons are used to give full valency for the fluorine atoms, and the 4 remaining electrons are placed on the xenon atom, giving xenon a total of 12 electrons, 4 more than an octet. It is estimated that over half of all known molecules are organic compounds, which means they are carbon-based. And virtually all organic compounds are formed from elements that adhere to the octet and duet rule. Therefore, we can take a slightly different approach when drawing Lewis structures for organic compounds. Common elements within organic compounds are carbon, hydrogen, oxygen, and nitrogen. Examining the Lewis dot structures for these atoms tell us how many valence electrons are present and how many are needed for full valency. For example, nitrogen has 5 valence electrons and will need 3 more for an octet. It will gain these 3 additional electrons by forming 3 covalent bonds. Remember, each time a bond is formed, an atom has access to an additional electron. Thus, if an atom needs n electrons for full valency, it will form n bonds. Let's start our alternative approach to drawing Lewis structures by examining ethane, C2H6. Each carbon has 4 valence electrons and needs 4 more electrons for full valency. Thus it will do this by forming 4 bonds. Each hydrogen atom has 1 electron and needs 1 more, thus it will form 1 bond. Notice that when we are drawing the atoms, we are keeping the appropriate number of valence electrons associated with each atom. After the carbons are connected, we see that each carbon needs 3 more bonds. Placing 3 hydrogen atoms on each carbon atom forms the 4 bonds necessary for each carbon to obtain full valency. In the next example, ethene, C2H4, has 2 fewer hydrogen atoms. Thus, when we try a similar approach, we find that full valency for the carbon atoms has not been achieved. Each carbon now only has 7 electrons. However, pulling the 2 electrons down so that they form the second bond does give full valency, or the required 4 bonds for each carbon atom. In our last step, we redraw the final structure to get atoms as far apart from each other as possible. Think of this as the atoms attempting to minimize repulsions. It is worth noting that this final step will be done for all subsequent examples, if necessary. A similar approach is needed for acetylene, C2H2. Again, we see that the only way full valency can be achieved is to bring down electrons for additional bonds between carbons. The double bond brings the atoms closer to full valency, 7 electrons around each carbon atom. Therefore, if we bring down the second set of electrons to form a triple bond between the carbon atoms, full valency has been achieved, which is 4 bonds for each carbon atom. Using this same approach for C3H6 means we first connect all of the carbon atoms. When we attach all of the hydrogen atoms, we realize we are short 2 hydrogens. Thus, we can swing 2 electrons down to form a double bond, and we have drawn a solution to the molecular formula. However, if we place 2 hydrogens on each of the carbons, we can draw another solution by swinging the 2 N carbons down to form a cyclic structure. A quick check shows that each carbon now has 4 bonds or full valency. These 2 structures share the same molecular formula, but different gross connectivity, and are called structural or constitutional isomers. In addition, structural isomers have different chemical and physical properties. Before proceeding, it is worth our efforts to learn about degrees of unsaturation. A fully saturated hydrocarbon follows the CnH2n plus 2 formula, where n is an integer. For example, C2H6 is fully saturated. Recall that when we assembled the Lewis structure, there was enough hydrogen atoms to give full valency for each carbon. However, C2H4 is short 2 hydrogens, and we say it has 1 degree of unsaturation, which fits the general formula CnH2n. In addition, C3H6 had 1 degree of unsaturation, which also fits the CnH2n formula. Therefore, if a degree of unsaturation exists, one can introduce a double bond or a ring. The C2H2 example fits the CnH2n minus 2 formula for 2 degrees of unsaturation. 2 degrees of unsaturation are satisfied by a triple bond, 2 double bonds, a double bond and a ring, or 2 rings. Looking down the general formula column, we see that each time a degree of unsaturation is introduced, 2 fewer hydrogen atoms are present. Calculating degrees of unsaturation for a given molecular formula helps us develop a logical plan before drawing Lewis structures. Examining the molecular formula for C3H4, we see that there are 2 degrees of unsaturation, which means we can have a triple bond, or a ring and a double bond, or 2 double bonds within the carbon skeleton. However, we do not have enough carbons to form 2 rings. The minimum requirement for 2 rings is 4 carbons. With our carbon skeletons assembled, we can simply place the 4 remaining hydrogen atoms on each of our structures to give 4 bonds to each carbon. Thus, there are 3 structural isomers possible for C3H4. It is worth mentioning that the 3 solutions were obtained quite easily by first deducing the degrees of unsaturation. Interestingly, the cyclic compound with a double bond fits our set of rules. However, it is too strained to exist at room temperature and can be eliminated. For C4H8, we calculate that there is 1 degree of unsaturation, which means we should try and draw solutions with a double bond or a ring. After connecting all 4 carbons, we see that we can introduce a double bond between carbon 1 and 2, or between carbon 2 and 3. Placing the remaining 8 hydrogen atoms on our carbon skeletons yields 2 structural isomers. Now let's set out creating solutions which incorporate a ring. With the 4 carbons attached, we can create a 3 or 4-membered ring. Attaching the remaining 8 hydrogen atoms to these cyclic compounds yields 2 more structural isomers. However, upon closer examination, we can also draw 1 additional structure, a geometric isomer. Geometric isomers have the same gross connectivity, but differ only how the groups are oriented in space due to hindered rotation about the doubly bonded carbons. In addition, they also have different chemical and physical properties. When we draw an imaginary line along the axis of the double bond, and then compare groups on each side using the Cahn-Ingold Prelog sequence rules, we can determine if the groups of priority are on opposite sides, called the trans-isomer, which is often abbreviated E. Alternatively, the groups of priority can be on the same side of the imaginary line, called the cis-isomer, often abbreviated Z. Therefore, a pair of geometric isomers is possible for one of our solutions, which afford a total of 5 solutions. Now let's begin to examine increasingly more complicated organic molecules. For example, C2H6O. Oxygen has 6 valence electrons, thus it will want to make 2 bonds to gain full valency, either 2 single bonds or a double bond if a degree of unsaturation exists within the given molecular formula. Ignoring the oxygen for a moment, we have previously seen the solution for C2H6, and there are no degrees of unsaturation. Thus, there will be no degrees of unsaturation for C2H6O, which means the oxygen can only form 2 single bonds and not a double bond. Simply inserting the oxygen atom between the 2 carbons yields one solution, dimethyl ether. Notice that all atoms have full valency, and as a quick check, we see that each carbon has 4 bonds. Each hydrogen atom has 1 bond, and oxygen has 2 bonds. We can also insert the oxygen between a carbon-hydrogen bond to yield a solution, ethanol. At this point, it is important to understand equivalent hydrogen atoms. In this example, all 6 hydrogen atoms are equivalent. We can prove this by inserting the oxygen between a different carbon-hydrogen bond. When we do this, we see that the 2 compounds have the same gross connectivity and are superimposable. Thus, we can create 2 structural isomers when inserting the oxygen atom. When dealing with saturated organic compounds that contain oxygen, it is often more convenient to first ignore the oxygen, draw all possible solutions, and then insert the oxygen to yield unique isomers. Now let's apply all of these concepts to C3H6O. Ignoring the oxygen, we calculate 1 degree of unsaturation, which means we can have a double bond or a ring. We first set out to draw all of these solutions, ignoring the oxygen atom, a double bond, and a 3-membered ring. Utilizing all 6 remaining hydrogen atoms yields 2 intermediate solutions. Now we play the oxygen insertion game to yield as many structural isomers as possible. We see that we can insert the oxygen atom at 5 unique sites within the intermediate solution with the double bond. Note that the last 2 compounds are geometric isomers. And we can insert the oxygen at 2 unique sites within the cyclic intermediate solution. In addition, we can construct a 3-membered ring with the oxygen atom. With 1 degree of unsaturation, we can also have a double bond between an oxygen atom and a carbon atom. Remember, oxygen forms 2 bonds to obtain full valency, either 2 single bonds as shown within the previous solutions, or a double bond if a degree of unsaturation exists. Thus, we should connect all 3 carbon atoms, followed by adding a double bond oxygen at all possible sites to account for the degree of unsaturation. At carbon 1, and at carbon 2, which yield 2 more structural isomers after the hydrogen atoms are attached. Therefore, a total of 10 structural isomers can be formed. It is worth mentioning that our logical stepwise approach affords all possible isomers, while a hit-and-miss approach may have missed 1 or more of these solutions. Another common element used when drawing organic Lewis structures is sulfur. Because sulfur is in the same family as oxygen, it also has 6 valence electrons. Therefore, it can be treated in the same manner as oxygen. For example, if we were to draw all the Lewis structures for C3H6S, we use the same approach as we did for C3H6O. Ignore the sulfur, calculate the degree of unsaturation, draw intermediate solutions ignoring the sulfur atom, play the sulfur insertion game, and if there was at least 1 degree of unsaturation, we would draw double bond sulfur-carbon compounds to yield all the possible structural isomers. Now let's look at organic compounds that have nitrogen in their molecular formula. Recall that nitrogen has 5 valence electrons and needs 3 more. Thus it will form 3 bonds, either 3 single bonds, a single bond and a double bond, or a triple bond, depending on the degree of unsaturation. When drawing structural isomers for C2H7N, we will first connect the 2 carbon atoms and nitrogen atom. There are 2 possibilities. Now we see that 7 hydrogen atoms are required for full saturation, which is how many we have. If you add a nitrogen atom to the formula, you need to add an additional hydrogen atom for full saturation. When drawing the structural isomers for C2H5N, we will first connect the 2 carbon atoms and nitrogen atom. Again, there are 2 possibilities. As we have already seen, 7 hydrogen atoms are required for full saturation. However, we are short 2 hydrogen atoms, which is 1 degree of unsaturation. Thus, we can incorporate a double bond or a ring. We will begin our logical approach to this problem by introducing a double bond to afford 3 unique intermediates, or a ring to both of these carbon-nitrogen skeletons. After adding the remaining 5 hydrogen atoms, 4 unique structural isomers are easily afforded. Again, all of the solutions were obtained quite easily by first calculating 1 degree of unsaturation, which helps us develop a logical plan before drawing Lewis structures. Understanding why bonds form and what types of bonds will form between the various atoms is essential when studying chemistry. And with a little practice, your ability to draw structural isomers can be mastered.